So if I place this circular loop of wire in a region of space where there is no magnetic field, and then over time, I allow that magnetic field to build up to some value so that it fills the space with a magnetic field in this direction. And because I need to have something for you to do and feel a little bit more superior, let's assume that the radius of the loop is 0.2 meters. Okay. The radius of the loop is 0.2 meters. And let's say that it makes this transition in 0.25 seconds. My first question for you is, using all the information that's there, tell me the size of the EMF. You don't need any more information I presented to determine the size of the EMF. You may not know how, but I'm telling you that you have everything you need. If you don't know where to begin, begin by finding an expression of the flux. That's where you begin, which really isn't rough. That's something you could do. So what'd you get for your expression of flux? This is what I got. The magnetic field is uniform over the region of space where the loop is. So I have to add up how much magnetic field passed through the area of the loop. The loop is a circle with radius 0.2 meters. So the flux will just be the size of the magnetic field times the area of the loop. I have the loop suspended in such a way that it is in line with the magnetic field. So it's cosine of 0 degrees. So that is the flux. Now, if you want to find the EMF, you need to find the rate of change of the flux. So there's only one loop. I'm going to leave the N out. And that's going to be minus d dt of b pi r squared. Which of those things stays the same over time? Pi r squared. So minus pi r squared. And now dB dt. Well, if it changes in a uniform way, that'll just be 5 Tesla minus 0 Tesla divided by 0.25 seconds. That's what's changing, is the magnetic field. So this is dB dt. Again, we're assuming a uniform change in the magnetic field. Now, the rest of this is plugging in numbers, the least interesting part of this. Four times 5 is 20. There we go. I think that's all right. 0.04 times 20, 8. And 8 times pi, so 24, plus some change. What's that? 0.08 times 20 is probably not. Yeah, you're probably right. Well, I don't have a calculator. So negative 2.5, you said? And that's going to be, remember our units here, it just ends up being volts. Now, we're only going to get those 2.5 volts for a quarter of a second. So, although we might get a lot of voltage for that quarter of a second, it's not going to last very long. The issue is now, what is the direction of the current in that loop? Is it going to be clockwise or is it going to be counterclockwise? And it wants to tell you here that the voltage will be in the opposite direction of the change in flux. So hear me out. I have a building flux that's building out of the page. To try and prevent there to be a flux out of the page, the current that's created has to create a magnetic field that is into the page. That's how Lenz's law works. That the direction of the applied EMF opposes the change. So again, since the magnetic field is building out of the page, our current has to be in a direction to create a magnetic field into the page. That's how this works. Let's try another one. All right, so I have a square loop in a region of space, and I have a machine that can produce a magnetic field that will build with a rate of 12t plus 4. So that at time 0, the magnetic field is 4 Tesla, and you can do the math on the rest of it, but the magnetic field is going to build 12 Tesla every second. That's what the expression is. First, what EMF would be produced in a square loop of side length 4 centimeter? And what direction would you have to apply the magnetic field? Into the square or out of the square in order to have a clockwise current? Everybody understand the dynamics of my question? I'm asking first for an expression, a calculation. But then I want you to tell me, is it into the board or out of the board? Are you giving me an answer or do you have a question? Go ahead.
Are you asking for the magnetic field that is created by the square or the one that's there initially?
I'm asking for, if I have the machine that generates this magnetic field, do I direct that magnetic field into the loop or out of the loop to get a clockwise current? There's only 9 minutes left. If I was to just call on any one of you, how many of you feel uncomfortable answering my question for what the EMF would be? Be honest. All right. Did you start with the flux? So flux doesn't have anything to do with time. It has to do with geometry. So I don't know the direction of the magnetic field, but I know it's either going to be a field of dots or a field of X's. But the magnetic field is some value in this region of space. I know it's uniform. As long as my loop is aligned with the magnetic field, my cosine is going to be 1. And as long as the magnetic field is a constant, I can pull it out of the integral. And what will be left is me having to calculate the area of the loop that is exposed to the magnetic field. So that's it. Or if you want, side squared, this will be an expression for the magnetic flux. Now, using that in the next step isn't a huge deal either. I am looking for the rate of change of the magnetic flux. There's one loop, and the negative sign is going to tell me direction, so I can ignore the negative sign. So my EMF is going to be the rate of change of B times S squared. Is S squared changing over time? No, pull it out of the derivative. Is B changing over time? Put in your expression. You have an expression that has a T in it. Now calculate the derivative. Since S is 4 centimeters, this is 0.04 times 12. This will be in volts. So at 0.048. Oh, well then it's not 0.048. Again, you start by calculating flux, and then you take the time rate derivative of the flux. Something's got to be changing for there to be an EMF. Now, there's a lot of extraneous information here. The 4 didn't matter, and the length of time didn't matter. Be used to that. However, to get the answer, if I want a clockwise current is going to produce a magnetic field that is into the board. This is a current that's produced in opposition to the change. So I want the magnetic field to be building in such a way that it's building out of the page and getting bigger. The slope of this function is positive. So it's an increasing magnetic field. That's important because if I put 4 minus 12t, it would have been the opposite there, so it would have been a decreasing magnetic field. So understand, my function was increasing. So I need to choose a magnetic field that would increase out of the page because the current that's produced wants to oppose the change in flux. Lenz's law, is it a little challenging? Are you catching on to it a little bit? Do you need another one? Because I've got more, but they get harder from here. Yes.
So, when exactly are we allowed to just disregard the negative? Because in the previous example, we kept it. I'm not sure what's the thing.
What does the negative tell you?
The direction.
Okay, so Can you interpret the direction? I don't know what you're asking. Why don't you, do you mean like I left the negative in here so that I could remind myself to go deal with the direction of the answer? The magnitude of the answer is 2.5 volts. Negative 2.5 volts doesn't mean anything, does it? Because if a potential has a positive or a negative, then you expect there to be a point of reference for what the change in potential is. I have a loop. There's no point of reference, right? If it's an increasing potential going from the floor to the top of your desk, then you could say positivity or negativity. You're providing reference about where zero is and whether you're increasing your potential or decreasing. I have a loop. Where am I increasing from or to? That negative sign is a reminder to go over here and say, okay, what is the direction of my EMF? Does that make sense? Okay. I would not put the negative sign in a numerical answer when asked for the voltage from Faraday's law. All right. You're welcome. I didn't understand the question at first, and now I do, and that helps. This is a favorite. So what I mean by that is this is one that is within our abilities to do, requires a little bit more advanced mathematics. So it tends to be one that is a favorite of people who like to give tests and see if you really know what you're talking about. Let's assume that I have a current in this wire. Doesn't matter what the current is right now, just a current in the wire. Or, heck, let's do this. It's AT squared is the current in that wire, where A is in Tesla per second squared. Just some function. Everybody okay? So the A is not acceleration, it's just some constant that's in Tesla per second squared. I have a rectangle here next to the wire. The rectangle is length L, height W, and is a distance Z away from the current carrying wire. Yep. Amperes. Can't do anything right today. Amperes per second squared. Glad I'm recording this. Can't wait to post this one. Get some of them fun comments. Would you agree that there's a magnetic field in the region of space where this current loop exists? And would you also agree that the magnetic field is changing with respect to time? The current's increasing, so the magnetic field's increasing. In fact, I know right now that the magnetic field is out of the board on this side and into the board on this side by just using my right hand rule. And well, I guess I'm assuming that the current's in this direction. However, I know from Ampere's law that the size of the magnetic field depends upon how far away from the wire we are. So although it's concentrated in the beginning, it gets less and less as we get further away from the loop. Now, listen, folks, I want this tomorrow. I want you to make a reasonable attempt at computing B.DA. I will give you a hint. Break this up into small rectangles that are of length L and width DZ, so that the area is L times DZ. Then you can integrate from Z to Z plus W. try this, please. Try to put the stuff in here that you have. You'll know you've done it right if you get a log in your answer. I'm going to write that out, not because I don't think you understand it, but because I want you to understand which words I'm using. You have to assemble, put together a sum. An integration is a sum. So your job first is to find out how much one of the parts is. Right? You're going to be adding a bunch of parts together. So find out how much one of them is. That's what the start of this is. So take what we have as flux and perhaps think of it as, what's a piece of flux look like? I know, understand that you're all in calculus and you understand how to do calculus things. But as I've tried to indicate before, calculus doesn't assemble this part. Calculus gives it to you pre-assembled. Your job is just to act on it. Assembling the sum, putting together the pieces that make this a sum, that's what this class is really supposed to serve. Calculus just backs up the final portion of this, where you say, okay, there's my sum, integrate it now. You don't get that part in calculus. So let's assemble our sum. And I'm just gonna focus on one of these rectangles. I don't need all of them, I just need one of them. So I'll pick the one that I started with first, the one that's right there. Well, this area we talked about yesterday, it's a rectangle. If you have DA, you're gonna be making something that's an area. I picked a rectangle because I know that the amount of magnetic field here is the same as the amount of magnetic field here. So I know along the length of this rectangle, the magnetic field is the same everywhere. But I also know that it changes when I go from here to here to here. So I'm assuming that for the time being, my DZ is really small and I'm just looking at the magnetic field basically along this line. I'd like to think of this DZ as a line. So it's just really, 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 really thin. I draw it thicker than that because I want to have something I can at least look at and kind of touch and feel so that I understand that it's an area, but even the line I've drawn is too wide for that. The idea is that there's just a point in space where the magnetic field is the same everywhere along that point. So this one line has one magnetic field. And that magnetic field we have from mu naught I over 2 pi r, where r is the distance from the wire to this location. That's why we know the magnetic field isn't constant. Now, I'm going to take that away because it's already written up there, just hidden. There. So let's go back to our sum. I have an expression for the magnetic field, and I'm going to sub it in here. It has to do with what says R there, but we're not using R as our measurement in our expression, so I have to translate this equation. This is happening to us a lot, where we're having to translate the equation. Which of the things about this equation apply, and which of the things is a placeholder that will have to be replaced? Well, mu naught, that's a constant. I is a placeholder. It will have to be replaced, right? We don't have I in our function. We have a times t squared. So I know that that's something that's going to have to be replaced. 2 and pi, those are constants. They'll be fine. R, that's a placeholder. It's how far away from the wire you are. So that's going to have to be replaced with the variable I'm using in my problem. Now, I chose to use Z.
The problem with using z is that z is a specified value here. So it's hard to use z. And when I sent you away saying z, I'm not sure that was a good idea. I probably should have used something not connected to the problem in any way. R probably would have worked better than z. I'll assume responsibility for that. We're pushing fast at the end there. So I'm gonna just write this not as z, but I'll leave it in terms of r, the distance away from the wire, and that way I can use this z that's over there later in the problem. It's not a problem to use a variable name twice like this, but z was specified. So I'm gonna leave this as a different variable just so I don't get them confused. Is that okay with you guys? And do you understand why I'm making that acknowledgement? So mu naught I over 2 pi r, whoops, not I, at squared over 2 pi r times, now I have to write my area in terms of something that I can integrate. We've been going through this a lot, but L is a constant, so working L in there would be great. But I'd also like to work in a variable that has something to do with where I am away from the wire, which is why we are changing from, we had there z to r, because r represents how far away from the wire we are. So I'm gonna write my area as L times dr, the width of my space there. Now, again, this is just a piece of the flux. Calculus is the voodoo that does the summation for us. You know, so that's all it is, but that's what we want. We want to use the voodoo that does the summation for us. We want the entire flux to pass through the rectangle, so I set my boundaries as z to w plus z. That's what my boundaries are. Our starting point and our ending point. Now, this part's calculus. It's procedural, and it's procedures we've done before. Most everything here has nothing to do with this integral. And for the most part, that's what you should see in a lot of these problems. Lots of constants that are just distracting. That doesn't make them easy to deal with, because looking through all of this and trying to figure out what's important, bless you, and what's not, that's work. That takes some patience. Do you know which of these expressions are important and which ones aren't? That's what you have to bring to the table here. That's, again, another part that hopefully calculus is teaching you. But most everything here has nothing to do with my integration. The only thing that changes as I go from z to w over z is r. That's the part that's changing. Everything else is the same. So mu naught a t squared over, L over 2 pi. And then now I have what I think is a pretty clean integral. So you go to calculus for months and months and months to do this part. Calculus doesn't do a whole lot to assemble this part. Can I assume you know what the antiderivative is here and what you're to do next? So I'm not teaching that part as much as I'm just writing that part down. I don't actually need to have the absolute value bars. It's been ingrained into me that I'm supposed to put them out there. But is there any way this can be negative? Is there any way this can be negative? No, so I mean, you don't really need them there. But it's just something that's been ingrained into me. It is always in your best interest to reduce or try and reduce any portion of your problem to a simpler form. Combining a natural log and not leaving it as a difference is a good idea. And even further, some of you I know when I walked around wrote this is 1 plus W over Z. It's fine. The only reason I generally don't do that is if you're going to be solving for a different variable, leaving it like this can sometimes be helpful, but 1 plus W over Z is fine. This is the flux. Is the flux constant? No. Not only does the magnetic field change as you go from one place to the other, but the flux isn't even constant because the current's not constant. But we froze this instant in time. So although the flux was changing, this instance of the flux doesn't depend on time. It depended on the area, where we were from the wire. So when you're doing the flux portion, just freeze time for that moment. Everybody understand? Because we're going to do another one in a minute, and I want to be really careful about how we approach it. Now, if I want the EMF, I got to take the time rate derivative of this and multiply by the number of loops and put a negative sign in there, all that stuff. Let's just find the magnitude. We'll worry about the negative sign in a minute. That's just going to be the time rate derivative of this entire expression. The only thing that matters here is something that has t in it or something that changes with respect to time. Now, don't be complacent here. It's quite possible you can have other things here that are affected by time. So you should be patient, cognizant, pay attention to the problem. But in this problem, the only thing that has anything to do with time is the value for t here. None of these other variables change. It's not like somebody's grabbing this loop and pulling it away from the wire while the current is changing. So it's not like Z is going to change. It could, but it's not right now. So I think we're okay pulling anything that's not t outside the integral. We get bogged down in the alphabet soup of these problems because there's letters everywhere. So although a better teacher might sit here and always just put the letters that you need to focus on in a different color, that's not how the AP exam's going to be. It's going to be in your pen or whatever the pencil you're using or the blackness of the toner that's going to be on the page. None of it will be in color, none of it will be special. And you'll pull out your equation sheet and nothing's going to stand out. It's all going to be just black toner on white paper. So you have to kind of evaluate it. When it comes down to it, the calculus portion of these problems shouldn't be all that challenging. That's the calculus portions of these problems. It's stuff that's built around that we're having to do our struggling with. Because now this is just going to produce a 2, right? And take us from t squared to t. So I can get rid of the 2 in the denominator there and get mu naught. You have to understand why this piece of software does such a terrible job scaling the pen size. I'm not changing it up here. I just zoom in and out, and suddenly I got big, thick pen size, and I didn't have big, thick pen size before.
Are you designing for different pressure?
No, I'm not. That's just it.
It feels under pressure.
Maybe. Under pressure because Mr. Shelton's doing all the talking, I guess.
Maybe there's a setting somewhere that controls that. Scaling field.
So again, you covered all 3, right? We can do what we did, change the current. We could rotate the loop, or if we say we're going to take this loop and pull it away, find where the flux is. Before anything is changing, just find where the flux is that you just solved. Well, that's right here. Right, that's just the flux. In the circumstance where we are pulling it away, this goes back to being just I, right? Constant current. But now this is what's changing. Can you do that problem? Right? This is an instant, it's at z, but if it's moving at velocity v, then v would be dz dt. That's the only thing that's changing. What if the loop is spinning? You know, we talked about the fact that the loop might be spinning. Well, then I and z stay the same. Where would the spin be? Well, hate to say it, it would be right here. Except likely, theta is an instant in time, right? Truthfully, theta might equal omega times t. Do you understand why I'm saying that? Because we're at a specific theta. But if it's spinning, we freeze it at that angle, and now we'd have to substitute omega t into our cosine here. All of these are just different ways to generate an EMF. By the way, is the magnetic field in our original problem getting bigger or getting smaller?
Bigger.
What's the direction of the current then generated? In the end, it's going to be clockwise or counterclockwise. So raise your hand if you think it's clockwise. Raise your hand if you think it's counterclockwise. So half the people raised their hand and the other didn't raise their hand at all. Nobody raised their hand for counterclockwise, but only half people raised their hand for clockwise. Is there a third option I'm not aware of? Or can I assume that the non-hand raisers either weren't listening, asleep, or don't know the answer? Remember, the generation of the current is to oppose a change. If the magnetic field is getting greater, the direction of the current must be creating a magnetic field that opposes the current magnetic field. So we need a magnetic field that is into the board. That has to be a current that is clockwise. Now, would that be true if the current was constant and we pulled the loop away? If the current was constant and we pulled the loop away, would we have a clockwise current or a counterclockwise current? Counterclockwise. Why? Because the magnetic field gets smaller as we go away from the wire. I want to maintain the flux. So I'd have to generate a magnetic field that is out of the page, and therefore current would have to go in the opposite direction.
It's both the current is changing and the loop is moving as well.
Well, if you have one where they have all that changing at once, I would strongly encourage you to look for whatever math deity you bow down to when you don't know what to do with a math problem, and pray in whatever form you generally do that they'll just give you some partial credit and pick one and wing it. They're not going to do that. And here's why. I'm going to have the one that's pictured there, which is trying to be a sideways view, but then a top-down view, just to make us understand that I'm dealing with just a single circular loop of wire, and our magnetic field is, uniform, but out of the page, something like that. So just stick that in the corner and put a couple of reference pieces on it, like there's a radius of R. Is that all right? Magnetic field B. We're going to take the loop and we're going to spin it, and it has a spin speed of omega. the rate it's going to spin. Let's first start with talking about the direction of the current induced. I think that's a hard question. So imagine, if you can, the way I've drawn this picture. And you're trying to figure out what direction the current will be. Can you all kind of agree that until we reach, say, here, the current's going to be one direction, and then while we go from here to here, the current's going to be a different direction? And does everybody understand why that is? If you don't, it's okay. I want to explain it. But if we're doing this direction, the flux is getting larger for a while, right? So that's got to be one direction of current. But now the flux is getting smaller for a while. That's going to be a different direction of current. So it changes right here, because now the flux is getting smaller and smaller and smaller, and getting smaller in the other, getting bigger in the other direction now, right? Getting bigger and bigger and bigger and bigger and bigger in the other direction. And now it's getting smaller and smaller and smaller and smaller and smaller in that direction. And then it's going to flip directions again. You guys kind of see what's happening? Direction on this one is a little tough, because as the flux is diminishing, the current has to go one way. As the flux is increasing, the current has to go another, and that's changing every pi over 2. You following that okay? So I'd say the direction on a problem like that is a challenge. And I think you can talk about the direction only when asked from like one angle to a 90-degree angle from there. You guys follow why I'm saying that? So like right now, if we talk about going from here to here, I think we could determine the direction. And it's not terrible. The flux is diminishing. So the direction of the current has to be to reinforce the current magnetic field, which would be, based on the way I'm seeing it, a current that would look like this if we're looking top down here. Because that would produce a magnetic field in the same direction. That does a good job. That gets us to here. So now when we go from here, to let go of that, I can't turn again. When we go from here to here, what's the direction of the current going to be? Right now there's no flux. I'm starting to build a flux that is, well, suddenly you can pick either direction as the direction of the area of your loop. So when you pick that, maybe you want to stay with the same area for your loop. So we could draw in here an arrow that represents the area of our loop. That way we can keep all that together so that we have at least something that we can kind of use as reference. Well, that doesn't turn like I'd like anymore. Yeah, you'll just have to use your imagination. So as we go this way, that dot product, of course, is getting smaller. This way we're going against the magnetic field, right? This would be negative flux if we keep the area the same, but it's getting larger and larger and larger, so it's got to create a current to try and prevent there being a magnetic field that is going in the opposite direction of that arrow. And then we get a cyclic process after that. They're only going to ask about one of those. They'll ask for one transition, and from there ask about the direction. They have not asked about the direction of the current in a loop like this problem in a long time. There's good reason to believe they probably wouldn't, because it's a fairly complicated system. What's just fine for them is for asking for you to come up with an expression for the EMF produced. And so let's do that part, because that's the part that's important to me. I'm going to purposely leave it at a bit of an angle. It helps for us to kind of conceive of the concept of how to do this. Let's start by recognizing that we start with flux. If you're asked for an EMF, start with flux. We have a magnetic field that is in one direction, but our loop is slightly cocked to the side. This is to produce a way of measuring or inserting the angle into this problem. We're going to freeze it at this location. And I'm going to recognize that, well, the area is never changing. The area is pi r squared the whole time. And the magnetic field is never changing. The magnetic field is B the whole time. But what is changing is the angle between B and A. That's changing. And because that's changing, I will have to put in something that works for the dot product. Now, we are told that it's spinning at omega. You have to bring to the table that theta equals omega times t. They don't have to tell you that. Does everybody understand why I'm saying that? Because this is just a straightforward motion equation without acceleration. All right, this is delta theta equals 1/2 alpha t squared plus omega times t. That's where this comes from. And for those of you who aren't currently in mechanics and maybe didn't have mechanics at all, we did this a little bit in AP Physics 1, but not very much. If it's not accelerating, the good news, it's on the equation sheet, if you know what all that gobbledygook means. Now, getting back to this, we still need an expression. I don't really need the integral symbol. By saying that dA is pi r squared, I'm taking the integral here to get pi r squared. I didn't say that out loud, but I should have. And I don't know why I wrote co theta when I mean to say cosine theta. There we go. I'll just say that I wrote it, but the screen didn't register it. My technology failed. I didn't fail. Now, I think it's a good time at this moment to go ahead and write in the cosine omega t. Now your EMF minus n times the rate of change of the flux. Leave out the n, leave out the minus sign. And we've got time rate of change of b times pi r squared cosine omega t. Again, step 1, find the flux. Freeze it in place, find the flux. Step 2, take the derivative with respect to t. Everything that is a constant comes out of this derivative. I assume you guys know how to do this derivative. So I know it produces another negative sign. Again, with the, what do you think the negative sign is about here? Nothing? Do you know that it produces another negative sign?
Yes.
Okay. What do you think it's about?
The direction.
Yeah, it's still about the direction of current. So I would not worry about it. You're going to have your magnetic field, you're going to have your pi r squared, or whatever the shape of your loop is. You get an omega here, and then you have sine omega t. First, do you realize that this produces a non-uniform EMF? That this EMF is changing all the time. That was okay, we've had non-uniform EMFs, but do you notice that it's cyclic, but how big the peaks are depends on how fast you spin it. So if you spin it faster, you get larger amounts of peak EMF. This is how we produce power in this country. And in this country, our power is at 60 hertz. You can convert that to an angular speed for radians per second. Europe is 50 hertz. And I don't know much about the rest of the world, but it's a combination usually of these two. We have 120 volts as our peak. That's how that measures at the outlets. You guys, you can pack up. Just hear me as I'm talking. Let's try one more. Yeah.